Hello, I'm Sébastien Bouchard. My co-authors are Yoann, Dieudonne, Andrzej, Pelc and Franck, Petit. I'm going to present you our article entitled Almost Universal Anonymous Rendezvous in the Plan. Rendezvous is the name given to a distributed task involving mobile agents. I'm first going to present you those mobile agents, the task of rendezvous and the model when considered in our article. Then I will give you more details regarding the type of the art and our contributions. Let's start with the presentation of mobile agents and rendezvous. Mobile agents are theoretical entities able to perform computations, execute an algorithm, observe their environment, and move in it. The environment we consider is the Euclidean plan. On the slides, the mobile agents are represented by this kind of picture. Several work consider mobile agents and differ in particular in the abilities the mobile agents are assumed to have. We build on a series of work which assume that every mobile agent can only observe its surroundings, that is, the closed disk centered at its position with a constant radius. It is represented here around the agent. Each agent has an internal clock. At each bit of its clock, the agent can choose either to move or to wait until the next bit. If it chooses to move, then it chooses some direction and travels in this direction until the next bit. Every agent is equipped with an unbounded memory. At each bit, the choice made by the algorithm can take into account the history of all the previous choices. Here, it chooses once more to move. It does so still at full speed. It travels the same distance as earlier. It can also choose to wait, in which case it just stays idle until the next bit, and so on. The most studied task involving these mobile agents is rendezvous. It consists simply in bringing together two agents spread in the plan with no idea where the other one is. One can think of this as making the agents close enough from each other to communicate and coordinate for some future task. In the model we consider, the mobile agents have several features. Feasibility and complexity of rendezvous could depend on these features. We need to take a closer look at them. We first identify the parameters which may differ between two settings, two instances of this task. Each agent has its own internal clock. Their periods may differ. For instance, here the period of the red agent is shorter than the period of the blue one. Moreover, the two agents not necessarily start executing the algorithm at the same time. There may be an initial delay. To study rendezvous in our model, we need global units for time and distance, for instance. The agent which starts executing the algorithm first is called agent A and used as a benchmark. The other agent is simply called agent B. The time period of agent A is used as time unit, and it's used to express the time period of agent B, denoted by tau, and the initial delay, denoted by t. These are two of the parameters we use to characterize the instances of rendezvous. This is it for time. Let's take a look at distances. The distances traveled by each agent during one of its periods may differ because they have different time periods, or because they have different speeds, or even both. We use the distance traveled by agent A during one of its time period as the distance unit. This gives us another parameter for the instances, v, the speed of agent B. Moreover, we use our distance unit to express the radius of the closed disk each agent is able to observe. The radius is the same for the two agents, and it is denoted by r. The remaining features of the agents, and thus the last parameters of the instances of rendezvous, are related to their local coordinate systems. Each agent has its own local coordinate system. We express the initial coordinates of agent B in the coordinate system of agent A. This gives us two other parameters of the instances, x and y. Another parameter is the angle between the x-axis of the agents. We call it phi. The last parameter is the chirality. Do the agents have the same clockwise direction? If they do, we say that chi equals 1, and over y we say that chi equals minus 1. Here the two agents have a different clockwise direction. That's why here chi would be equal to minus 1. That's it. Here are all the features of the mobile agents in our model, and thus all the parameters which can distinguish one instance of Rendezvous from another one. We represent every instance by a tuple of 8 elements, or the common radius of vision or communication of the agents, x and y the coordinates of the initial position of agent B, tau its time period, v its speed, phi the angle between the x-axis, between the coordinate systems, chi the shearity, which can be either 1 or minus 1, and t the initial delay. It's well known that rendezvous cannot be achieved deterministically in some instances. Assume that the two agents are identical, same period, same speed, no initial delay, x-axis parallel, and same shearity. If they act deterministically, they make the same choices, and their features do not make any difference. They are in symmetric settings. The distance between them does not change. In order to avoid this, the agents are often given identifiers which allow each of them to have a unique behavior, to break the symmetry. However, this is not the case in our study. Our agents are anonymous. And here is the first question we ask: which instances precisely are feasible? That is, in which instance can you achieve rendezvous deterministically? The second question is the following. Can a single algorithm ensure rendezvous for all feasible instances? Obviously, we are not the first ones to ask this kind of question. Before I present our contributions, I'm going to introduce two of the most related articles. The first article has been written by Sazovich and three co-authors. They define instance and feasibility of rendezvous in a different manner. They assume no initial delay and do not include the positions of the agents in the instance. Given values for tau, v, phi, and chi, they ask whether rendezvous is achievable regardless of the initial positions of the agents. Hence, if there exists some initial position from which rendezvous is impossible, they say that the instance, represented by the tuple tau, v, phi, and chi, is not feasible. However, there might exist some position from which rendezvous is achievable with these parameters. By including the initial positions in the tuple, we aim at being more precise than their study. The authors characterize the feasible instances with their definition. For instance, they show that if the agents have different time periods or different speeds, then rendezvous is achievable. Moreover, they provide a single algorithm which achieves rendezvous for every feasible instance, regardless of the initial positions. The other article has been written by one of my co-authors, Andrzej Pelc, and his postdoc at that moment. The first difference between the article and ours is the fact that they consider the generalization of rendezvous to multiple agents, in which case it's called gathering. However, let's take a look at their approach and results in our context with only two agents. They consider a subset of our set of instances. First, they only consider the instances that we call synchronous, for which tau and v are equal to 1, which means that the agents have both the same time period and the same speed. Among the synchronous instances, they also restrain their attention to the instances in which the local coordinate systems of the agents only differ by a translation. Phi is equals to 0 and chi is equals to 1. Their results are closer to ours, and I'm going to spend a little time describing them. They show that rendezvous is achievable if and only if the initial delay t is at least that thing, that is the distance between the initial positions of the agents minus r. 0, 0 is the initial position of agent A in its own coordinate system, and x, y are the coordinates of the initial position of agent B. Okay. They also provide a deterministic algorithm which works only if t is greater than that thing, the initial distance between the agents minus r. The difference is interesting. If t equals the initial distance minus r, rendezvous is achievable. There exists an algorithm, at least for this particular instance, which ensures rendezvous. But their algorithm does not manage to achieve rendezvous for all such instances, and they prove that there is no such algorithm. Let me explain a little bit some ideas behind these results. There is the same kind of phenomenon in our own results, and this explanation will benefit to the presentation. Okay, consider some instance. Remember that the authors of this article assume same time periods, same speeds, and similar coordinate systems. The algorithm gives the same instruction to both agents. The agents do not execute them at the same time because of the initial delay, but when executing it, they go in the same direction, spend the same amount of time moving, and travel the same distance. This means that the distance between the position of agent A at time 1 after this move and the position of agent B at time t plus 1 after the exact same move is equal to the initial distance. In other words, if A has come closer to B at time 1 thanks to that move, then it better achieve rendezvous before time t, because at that moment agent B starts performing the same move and thus start moving away from agent A. Agent A has a time window of length t in order to achieve rendezvous. The delay, the length of this time window, has to be long enough for agent A to close the gap, and thus at least the initial distance between the agents minus r. This allows agent A to end up moving close enough to agent B before agent B moves away by making the same moves. Okay, let's get back to our contribution. We study the instances of rendezvous in which the agents may have different time periods, speeds, local coordinate systems, and starting times. We managed to characterize the feasible instances. Of course, this includes the subsets of instances shown to be feasible by the two articles I have presented. On the first line, these are the instances studied in the article by Sajzovic and his co-authors. On the second line, those studied by the second article. More interestingly, we show that when the agents have different clockwise directions, even though, as shown by Sajzovic, some instances are not feasible, some are feasible. These are the instances for which the initial delay is at least some distance, on which I'll come back later, minus r. We provide a single deterministic algorithm for all feasible instances, but two subsets. A subset S1, already studied by the previous article of Andrzej, for which he and his co-author have shown that no deterministic algorithm can achieve rendezvous for all its instances. And a second subset, SU, similar to S1, in that it corresponds to the case when t equals some distance minus r. Just like for S1, we prove that there is no deterministic algorithm which can achieve a rendezvous for all instances of SU. I'm now going to focus on the contributions of our article, and more precisely on the synchronous instances for which chi equals minus 1. These are the instances which have been studied the least. This subset of instances consists of some non-feasible instances and some feasible ones. Among the feasible ones, there are the instances of subset SU, such that there is no deterministic algorithm able to ensure a rendezvous for all of them. I'm going to explain why some of these distances are not feasible, and why there is no deterministic algorithm for S2. Understanding what happens with these instances requires to understand the properties offered by what we call the canonical line. It is the line parallel to the bisectrix of the angle between the x-axis, this angle of measure phi. Proj A and Proj B are the projections of the initial positions of agents A and B, respectively, on the canonical line. On the following slides, for every time S, Proj A as well as Proj B with S in parentheses denotes the projection of the position of agent A as well as agent B at time S. I have depicted an instance of the first move for the agents. For agent A, this move is executed at time 0, at the very beginning of the execution, while for agent B, it is executed after the initial delay at time t. These moves allow them to get closer from the canonical line, but the distance between their projections, here and here, does not improve. It's still equal to the distance between the initial positions. In the case when the agents agree on the chirality, studied in the article by Andrzej and his co-author, the distance between the agents is not reduced at all when they make the same move. Here it's different. They can get a little closer when they get closer to the canonical line. Somehow, when the agents agree on the chirality, the gap that agent A has to cross is two-dimensional, and when they disagree, this gap is only one-dimensional, along the direction of the canonical line. And for every real I, the distance between the projection of the position of A at time I and the projection of the position of B at time t plus I is the same as the distance between the initial projections. Let's see what this means concerning the feasibility of rendezvous for these distances. Assume that rendezvous is achieved at some time s. This implies that the distance between the projections of the positions of A and B at time s is at most r. Now consider the projection of the position of agent A at time s minus c. In view of the property I have just explained, the distance between the projection of B at time s and the projection of A at time s minus c is equal to the distance between the initial projections. This implies that the distance between the projections of the position of A at times s and s minus c is at least the distance between the initial projections minus r. Yet, between times s minus t and s, agent A travels the distance at most equal to t, and thus so does its projection. This means that for synchronous instances in which the agents do not agree on the chirality, rendezvous is feasible only if the initial delay is at least the distance between the initial projections minus r. Moreover, if t is equal to this value, then between times s minus t and t, agent A has no margin of error. It has to go straight to agent B on a line parallel to the canonical line. This is not the case if t is greater than this value. Agent A does not need to go straight in the good direction as long as its projection travels a distance equal to this value. Assume that there exists a deterministic algorithm which achieves rendezvous for every synchronous instance in which the agents disagree on the chirality and t is equal to the distance between the initial positions minus r. That is, for all instances of set SU. Since this algorithm achieves rendezvous for every such instance, this algorithm has to move along a line parallel to the canonical lines of all these instances. However, these canonical lines are uncountable. This is impossible. This proves that there is no deterministic algorithm able to achieve rendezvous for all instances of SU. That's it. I'm now just going to conclude this presentation. We have studied the task of rendezvous of two mobile agents in all possible instances, assuming that the agents have possibly different time periods, speeds, local coordinate systems, and that there may be an initial delay between the beginning of their executions. Among these instances, we have shown which ones are feasible, that is, for which instances there exists an algorithm, even dedicated to this instance, which ensures rendezvous. We have designed an almost universal algorithm, an algorithm able to ensure rendezvous for all these feasible instances, but two small subsets, S1 and SU. These subsets are particular, since there is no deterministic algorithm able to ensure rendezvous for all of their instances. For S1, it had already been proved in a previous article, and we proved it for SU. Further work on this topic could consist in extending our results to gathering. This has already been done by Andrzej and his co-author for the synchronous instances when the agents agree on the chirality. But we could extend this to the larger set of instances we consider in this article. Thanks for watching the video.